In section 3.1, we solved systems by graphing. In 3.2, we're going to solve systems using algebra. Now there's two methods to solve systems using algebra. The first method is substitution. To use substitution, start by solving one equation for one variable. Notice that it doesn't tell us which variable to solve for. Pick the variable that's the easiest to solve for. Pick a variable whose coefficient is either 1 or -1. Once we have one equation solved for, take that equation and plug that equation into the other equation and solve for the remaining variable. So we're going to take our equation from 1, plug it into the other equation, and solve for the remaining variable. Now if we've done our math correctly, we should have one variable left, and we know what its value is. So we're going to take that value for that one variable and take that answer from 2, plug it into our equation from 1, and solve for the final variable. And our last step, check our answer. When we're solving a linear system, whether we're using substitution or linear combination, we should always check our answer. We shouldn't get any wrong answers. We should have this mastered. Let's use substitution to solve problem number 1. So step 1, solve one equation for one variable. We have 4 choices: x, y, x, y. We don't have to necessarily pick any of them, but we should pick the easiest variable to solve for. In this example, this first x is the easiest variable to solve for because its coefficient is 1. We don't always have to solve for x in the first equation. It just so happens that this system, we're going to solve for the first x. I don't want to pick the other variables because then I'm going to have to divide by the coefficient or multiply by the reciprocal of the coefficient, which is going to give me fractions, and I want to avoid working with fractions. I can do that, it just makes my math a little bit tougher. So I'm going to start with the first equation and solve for x. Excuse me, this should be a -3. Step 2 says, plug that equation into the other equation. So I know how big x is. X is 3y minus 3 big. So I'm going to hop to my other equation, 2x plus 5y equals -17. And I'm going to replace this x with what I know x to be equal to. I know that x equals 3y minus 3, so I'm going to replace this x with 3y minus 3, and I'm going to keep everything else exactly the same in my equation. Now if you notice, when I replace x with what it equals, I don't have x in my equation anymore. I only have y. So I can solve this equation now for y. I'm going to start by distributing the 2. Collecting my like terms, and solving. So I know that y equals -1. So I know one value. I know that y has to be -1. But I also know that x equals 3y's minus 3. So x is going to equal 3 -1's minus 3. So x is going to equal -3 minus 6, which means that x equals negative 6. Last step, check my answer. I'm going to use a calculator to check my answer. I'm going to take x and plug negative 6 in for x, and take negative 1 and plug negative 1 in for y into both of these equations. So I have negative 6 minus 3 times negative 1. When I hit enter, I should get negative 3, and I do. I'm going to take negative 6 and plug it in for x, and negative 1 for y into my second equation, and I should get negative 17. So I know that my answer, negative 6, negative 1, is correct. You shouldn't get these problems wrong anymore. We're to the point now where you can solve a two-variable system, check your answer, and make sure you have the right answer every single time. The other way to solve a system algebraically is using linear combination. You might have called linear combination elimination in your Algebra 1 class, but elimination is really linear combination. To solve a system using linear combination, step 1, multiply both equations by numbers so that the coefficients of one variable are opposites. So if we break this down, this doesn't tell us what we have to multiply by. We can multiply our equations by different numbers. They can be the same numbers. We can multiply by 1. What we need to do is multiply so that the coefficients of one variable are opposites. One's going to be positive and one's going to be negative. And the reason we do that is so that when we add the equations in step 2, our variable is going to drop out. And when our variable drops out, we're going to only have one variable left. And since we only have one variable left, we're going to know what its value is. So kind of like knowing the value in step 2 for substitution, we're going to have an answer for one of the variables in step 2 in a linear combination. Once we know that value, plug that value into either one of the original equations and solve. So now I should have the values for both for both variables, and I can check my answer. Again, when I'm using linear combination, I shouldn't get a wrong answer. If I can check my answer, I should be able to know whether or not it's right or wrong. And if it's wrong, I should be able to go back and fix it so I have the right answer. So let's solve problem number 2 using linear combination. Step 1. Multiply both equations by numbers so that the coefficients of one of the variables is opposite. It doesn't matter which variable I eliminate. It doesn't matter which variables I make opposite. In this example, my y's have a fraction. So I'm going to try to avoid working with my y's in this example. I'm going to work with my x's. So I have a coefficient of 5 and a coefficient of 1. To make those coefficients opposites of each other, I'm going to have to multiply by a negative number and a positive number. In this case, they're both positive, so I need to make one negative and one positive. So I'm going to multiply the first equation by negative 1 and the second equation by 5. The reason I picked negative 1 and 5 is so when I multiply now, 5x times negative 1 gives me negative 5x, and x times 5 gives me 5x. Now my coefficients are going to be opposites of each other. That's step 1. I'm going to distribute this multiplication to every term in my equation. So I'm going to have negative 5x minus 3y equals negative 2. And I'm going to multiply everything in this equation by 5. 5 x plus 3/5 times 5 is 3 equals 2/5 times 5 is 2. Now I'm going to add my equations together, and the reason linear combination works is when I add negative 5x and positive 5x, I get 0. They disappear. And in this case, negative 3y plus 5y also gives me 0. So when I add the left side of my equations, in this example, I get 0. Now normally this wouldn't happen. If I had a problem like this first one, I'm going to have a variable here that I can solve for, and I'm going to know what the value is. But in this example, my variables disappear. My variables drop out. So I have something different going on in this system. So I'm going to finish my problem and then interpret my answer. Negative 2 plus 2 is also 0. So I have a unique case here where my variables drop out, and I'm left with 0 equals 0. I'm left with an equation that's always true. This is an example of a system that has infinite solutions. If I were to graph these two lines, they would be coincidental lines. So to interpret a system of equations where my variables drop out, I need to look at what I'm left with and decide, is that statement always true or not? If it's always true, my answer is infinite solutions. Opposite of something being always true is something that is never true. If I have a system that the variables drop out and I'm left with a false equation, I'm left with something like 0 equals 10, 0 never equals 10. So that equation would be never true, and I would have no solutions. So whether I do substitution or linear combination, if my variables drop out and I'm left with a true statement, it's always true, I have infinite solutions. If my variables drop out and I'm left with a false statement, that's never true, I have no solutions.